So in this next segment, we're going to start to make some of these calculations more quantitative, especially establishing a relationship between the standard state free energy and the equilibrium constant and the standard potential of the cell. We've been talking a lot about when things are spontaneous or not, and this is the same conversation we just had with delta G and K, right? So there should be some relationship. So what is the relationship between them? Well, for a spontaneous reaction, one that proceeds in the forward direction with the chemicals in their standard states, then uh, it's going to be, they're going to have the free energy change, standard state free energy change negative, the equilibrium constant positive, and the standard potential positive as well. So all of those are true for a spontaneous reaction, and the quantitative relationships are as follows. So we already saw this in previous segments. So it turns out that the free energy is just is proportional to the standard potential of the cell, and is the number of electrons that are moving in the reaction. So if you have a balanced chemical reaction, this is where you do take into account the number of electrons, not in determining the standard potential of the cell. Faraday's constant is just it just says how many coulombs there are per mole of electrons. And then the gas constant is usually in joules per mole Kelvin, and all the units work out since volts is joules per coulomb. So given this definition, given this definition of the relationship between standard state free energy and equilibrium constant, this definition between the standard state free energy and the standard potential of a cell, you can just rearrange algebraically and find a relationship that the standard potential of the cell is going to be RT over NF log K. And you'll see this written in the book sometimes, 0.0592 N times log K, but that just is trying to do too much algebra. Why do you remember 0.0592 when that's only true at room temperature? Why not just use the actual formula that's true for all temperatures, which is RT over NF times the natural log of K. So that's the formula I'd recommend, because it'll be true at 60 degrees C as well. And you don't have to memorize all of these, right? Well, for this year, you don't have to memorize any of them, but you don't have to memorize all three. If you know any two, if you remember this one and this one, then you get this one for free, because it's just algebra to get together. So that's how they all relate. Different ways to relate the spontaneity of reaction. This one is always going to be true. The others are only true in terms of redox reactions, because if it's not a redox reaction, you don't have electrons moving back and forth, and you have no way to define the standard potential for a cell. So for redox reactions, all of these are essentially equivalent. They're just different ways of describing the same reaction. Because when it comes down to it, the electricity in a battery, the electricity coming from the cell literally is just the chemical energy you get by transferring electrons, and you just harness that to do electrical work. So these are all equivalent for redox reactions. So which statement is true regarding a redox reaction that has an equilibrium constant of K equals 1.8 times 10 to the fourth? So pause, and I'll let you think about that for a second. Okay, we're back. So K, 1.8 times 10 to the fourth, that means the reaction favors the products, which means it's a spontaneous reaction, which means that we have that the free energy of that reaction is negative, so it's one of these two, but that corresponds to a positive standard cell potential, so the answer is C. Just different ways of quantifying the same chemical situation. Okay, so use tabulated electrode potentials to calculate standard state free energy for the reaction below, and we have to decide if it is spontaneous or not. All right, so we'll again go to our standard table and look up these particular voltages. So let's go. And what we need is the reduction potentials of iodine, which is here, 0.54, and bromine, which is 1.09. Cool. All right, so we've got that information. That's all we need. Everything else is just going to be calculations. So let's go back here and write that down. What equation are we going to be using? So the equation we want to be using here is delta G, standard state, equals minus N, Faraday's constant times E for the cell. So we need to figure out E for the cell. So I2S plus 2E minus goes to 2I minus, and we just looked that up. Our reduction potential is 0.54 volts. And then bromine liquid plus 2E minus goes to 2Br minus. That has 1.09 volts, but we're actually doing the oxidation of bromine. So E, that's a weird place to put the standard state symbol. Let's put it where it belongs. Cell is going to be E reduction minus E at the oxidation, and that is 0.54 minus 1.09 volts, which is minus 0.55 volts. Right away, we notice that it's not spontaneous. We don't even need to calculate the delta G to figure out that, but let's actually go through and figure out the delta G. So we have delta G is equal to minus 2. Aha, so in this case, 2 electrons are transferred. So we have to multiply by 2. So that's essentially saying that we have 2, in 1 mole of this reaction, we have 2 moles of electrons times Faraday constant, 96,485 coulombs per mole of electrons. And then we have minus 0.55 volts, but remember a volt is a joule per coulomb, so those cancel, those cancel, those cancel. We get an answer in moles, 1.1 times 10 to the 5th joules, or something like 110 kilojoules per mole, although there's only two significant digits there because there's only 2 significant digits in our cell potential. So that is the free energy of this, a moderately sized free energy. That's a substantial amount of free energy. And so this is not, oops, there's missing there. This reaction is not going to be spontaneous at standard conditions. And specifically, that is going to be its delta G. If we knew the entropy, we could figure out temperature dependence as well. So that's the end of this segment.